without external magnetic field at low temperature. Okay, so without external magnetic fields, this means H equals 0. And low temperature, if you remember, beta is the inverse temperature, so low temperature means beta large. Okay, so let me give you a few recalls. So what we have seen is that for beta larger than 0 and H in R, there exists Gibbs states which are given by the limit of the Ising measure with plus boundary condition. And so this was just by monotonicity for the expectation of monotone functions. We had convergence of measures with plus and minus boundary condition towards a Gibbs state. And here you just needed gamma to exhaust ZD not to converge in the Van Hoff sense. Okay, and we have seen that this Gibbs measure are maximal in the sense that if I have another Gibbs state, okay, then the expectation of an increasing function is somehow sandwiched between the expectation under the plus Gibbs states and the expectation under the minus Gibbs state. So in particular, we have seen that because of this observation, we have uniqueness of Gibbs states which is equivalent to this. Okay, so if the magnetization, the expected spin at 0 is the same under the plus and the minus Gibbs states, then there is only one Gibbs state. Okay, so we are going to now focus on the case where, okay, and the last thing that we have seen that this thing, okay, it's equal to the derivative on the right of f and this thing. Is equal to the derivative on the left of f. Okay, so what we are going to do today is I will use coherent notation here. we are going to investigate the case where h is equal to 0. Okay, what we had seen in that case, if you look at m star beta, okay, which is just this thing. Okay, we have seen that this is an increasing function. Okay, so in particular, if you define beta c as the infimum of beta such that m beta is larger than 0, what you have is that m star beta is positive for beta larger than beta c. Okay, basically. Okay, so basically we expect to have a picture like this, where you have a critical temperature beta, below which you don't have magnetization. Okay, so below which you have, yeah, okay. So below this, above this temperature, but below the parameter beta c, you have 0 magnetization, so uniqueness of Gibbs states. And above, you have positive remnant magnetization, and therefore, you have at least 2 translation invariant Gibbs states, 2 ergodic Gibbs states. Okay, and I mean, the fact that m star beta is non-decreasing almost gives you this picture, but there is one crucial thing missing. Basically, you need to show that beta c, well, is not 0 and is not infinity. Okay? So what we are going to show today is that m star beta is positive for beta large. Well, in fact, we are going to prove a little bit more. We are going to prove that m star beta tends to 1 when beta tends to infinity. Okay, so this means that even if you don't have an external magnetic field, when beta tends to infinity, basically, even though you're in the infinite volume limit, so the boundary is infinitely far away, you still feel in very much the influence of the boundary, since like almost all the spins wants to align with the boundary. This is what this says. Okay, like this neighbor, when beta is large, the nearest neighbor interaction is sufficient I mean, is sufficiently strong to travel long distances. Okay, so this is the main theorem of today. We need d larger than 2 because we have already proved that this theorem is actually wrong in dimension 1. So for d larger than 2, what we have is that the limit when beta goes to infinity of m star beta is equal to 1. this is due to pi loss. Okay, so any question about the statement? Okay, so the idea okay, so what we are going to prove is that actually we are going to find a bound for the probability of the spin at 0 to be negative. And this bound will be uniform in lambda, and it will be small when beta goes to infinity. So what we are going to do is we are going to show that there exists delta beta with limit when beta goes to infinity of delta beta, which is equal to 0, such that for all gamma, mu lambda beta 0 plus of the probability that sigma 0 is equal to -1 is smaller than delta beta. Okay, and well, why is this sufficient? Well, if you look now at this, this is equal to the limit when lambda goes to ZD of this. And this is simply mu lambda beta 0 plus sigma 0 equal plus minus mu lambda beta 0 minus sigma 0 is equal to minus. And from this, we get that this is larger than 1 minus 2 delta of beta. Okay, because this thing is nothing else than 1 minus 2 mu lambda beta 0 minus sigma 0 is equal to -1. Okay? Okay, and maybe one comment about this result. I mean, this result is really what tells you that, what explains like this phenomenon of that the magnet keeps the magnetization at low temperature when you turn off the magnetic field. Because basically what you're doing is you're submitting a magnet to an external field, so it takes magnetization m beta h. Then you turn the magnetic field, so what it means is that you kind of make h tend to 0, but in a positive manner. So the magnetization you get becomes this one and remains positive if beta is sufficiently low. Okay, this is the idea behind Curry's experiment. Okay, so the idea for the proof is to look at the interfaces that separates plus pins from minus pins. So this is possible to do that in any dimension, but we are going to do this in dimension 2, and then we are going to use some other argument to extend the result to dimension larger. Okay, so I mean, it's mostly because things are less cumbersome in dimension 2, but this is theoretically you can do this in any dimension. Okay, so. Okay, so the first thing we need to do, okay, so we're going to look at the contour representation of the easy model. So the first thing we are going to do is to rewrite the Hamiltonian. So from now on, I will, since h is equal to 0, for this lecture, I will just not write h. Okay, so I will just forget about this 0. So first thing we will do is rewrite the Hamiltonian. So if you remember, our Hamiltonian is the sum over edges in lambda of sigma x, sigma y, plus, well, the sum over edges on the boundary of sigma x, okay, where here, with some abuse of notation, I always consider that x is the one which is inside lambda and y is the vertex which is outside lambda. I have no eta y here because I have plus boundary condition. So what I'm going to do is that instead of considering this Hamiltonian, I will consider this one. So I'll put a bar. And so I will put a minus here. Then I have 1 minus sigma x, sigma y, minus beta sum over x, y, in delta y, sigma x, 1 minus sigma x. Okay. So the change there is between the two things is just I'm adding a constant. You see, I'm just adding beta per edge in the box and also beta per edge in the boundary. Okay, so this doesn't change my model actually. Okay. So what I have is that mu lambda beta plus sigma, it's really exponential h bar lambda beta plus sigma over z bar lambda beta plus, where, well, this thing is what I need to have a probability, okay? So when I'm doing this, I'm not changing the model. It will just be more convenient to work. You seem very puzzled. The sign of the muse doesn't match, yes, because this is this is plus time minus 1. I'm taking the expectation. So it's plus 1 times the probability that sigma 0 is equal to plus 1, plus minus 1 times.
It's not correct, because you're using the divisible quality for the mu minus, but it's for mu plus.
Ah, no, yes. So here there is a plus. Yes. Okay. Here I'm not changing anything, but you're right. Here there is a plus. Taking the expectation with respect to, this is the notation for expectation with respect to mu plus. Okay, so now let me come back to this. So why do I want to rewrite the Hamiltonian this way? Well, here I want to say that basically, each time I want to have, okay, so if you look at this thing, this is equal to 0 if sigma x is equal to sigma y, and this is equal to 2 if sigma x is not equal to sigma y. Okay, so basically what we are saying is that each time you want to have a disagreement between neighboring spins, this has an energetic cost of 2 beta. Okay, so this is penalized under our measure. Okay, and okay, this is exactly the same thing. Okay, except that here sigma y is given by plus 1 because y is on the boundary. Okay. So now what I want to do is transform, well, not really transform, but have a different look on spin configurations. So So let me try. I think if I do 6 by 6, I might be fine. Okay, 6 by 5, it will be fine. Okay, so let's imagine that we have a spin configuration. So recall that we have plus boundary condition. Okay, let the plus be red. I think this is and okay, let me define configuration like this. Okay. So here, what I have done implicitly is I have identified the sides of my lattice with squares. Okay, so what I've done when I've done that is really I have drawn the dual lattice already. Okay, so now what I want to do is when I have a spin configuration, I will associate to it an edge configuration on the dual lattice, okay? Simply by, if you want, opening all edges that are between opposite spins. Okay, so when I have an edge which is basically the dual edge of the edge which is dual to a disagreement edge on my primal lattice, then I just open it. So can you see green? Okay, I will just make it a bit fat. So. Okay, and then what I can do two things. So the first thing I can do is erase the lattice. So, just erase my spin configuration, just keep these green things. So yes. Okay, so basically, if giving you the green edges or giving you the spin configuration, I claim that this is the same thing. Well, if I give you the set of green edges, basically, you can recover the spin configuration by saying, well, I start from the boundary condition, so here I have plus, and each time I cross a green edge, I just change the sign of the spin. Okay? And of course, okay, here, what you obtain here, okay, so the graph induced by green edges as degree, as even degree on all vertices. This is an important observation. Okay, well, the idea is that if you look at what happens locally, you don't have that many possibilities. Well, either everybody has the same spin. In that case, this dual vertex will have degree 0. Okay? Or you have something like this, or like this. In which case, the vertex will have degree 2, okay, or we'll have something like this. Okay, and basically I've drawn all the possible pictures modulo symmetries, okay? I mean, you can just reverse all the spins, and you can rotate your pictures, and you get all the possible. Okay. So now what we can do, I mean, we can just add one extra step. So I would like to define this graph, this green graph, as a family of loop. Okay? So which I will call contour. And here, it's not completely obvious how to do so. So you would like to say, OK, so clearly, I cannot split that into a set of self-avoiding contours, OK, self-avoiding polygons. Yeah, here it's not completely obvious how I split this, OK? So what we are going to do is to fix a rule, OK, on how to split our contours. And it's a bit arbitrary. You could, but each time we see a vertex of degree 4, OK, what we are going to see is that actually it's really two paths that don't touch. Okay, and that they are going, I mean, they are separated in this manner. Yes, and I've taken the. Okay, so basically, what you get here is that okay, this thing is a loop, and this thing is a loop. Okay, so basically, using just this operation from a spin configuration, you get a loop configuration. And okay, I won't go too much into details there, but provided that you really define well what you mean by loop configuration, this transformation is bijective. You don't really lose information there. Okay, it's not crucial for the reasoning, but basically what I'm saying is that you can see the Ising model now as a measure on sets of loops instead of as a measure on spin configurations. Okay, so okay, I made lots of drawing and I wrote not a lot. Are the definitions clear? I mean, is it clear how I define the green edges and how we define these loops? Okay, so okay, okay, I'm saying loops. I should say contours. Okay. So now, given a spin configuration, I will associate to it a contour configuration. Okay. So a contour configuration is just a set of contours. Okay, whose cardinality is, I mean, it depends on n. And what's a contour? Well, okay, so contour. It's a set of dual edges which induces a connected graph which is, let me, okay. A set of dual edges which induces a graph where all vertices have degree 2 or 4. So when I mean it induces a graph, what I'm implicitly saying is that I'm considering the set of vertices that are adjacent to one of these edges. Okay, it's kind of implicit when I'm saying that all the vertices have degrees 2 and 4. And which remains connected after applying the deformation rule. Okay? So, you know, well, I just, it's not really, I don't know. I don't really like the idea of manipulating a concept without having a proper definition. So this is the reason why I'm writing this. And this definition is pretty much what you get out of the construction. Like, you took the graph induced by green edges, you applied this rule, and then you splitted this graph into connected components. Okay? What is a bit annoying in this definition is that it's not very analytic. I mean, like, okay, this part is, it might seem that we are. So what I can leave as an exercise is give a more analytic definition. But okay, it's not really an easy task. I mean, basically, you're considering, maybe the right definition for a contour is to consider a sequence of edges that are adjacent to each other, and then you have to quotient it by the right relation so that you're not really considering, I mean, that the sequence starting from here or starting from here, they are the same. And then you have to add something so that, well, you make sure that, I mean, clearly, for instance, this thing here is not a contour, okay? Because here I've not respected the rule when I did the drawing. Okay, so you have to add a rule for this. Okay. So, now I can go to the core of Payer's argument, and it's and it's something quite general that you can apply to other models in statistical mechanics. And what is it? It says that the probability of a given contour appearing in gamma sigma is decays exponentially with its length. Okay, or that the probability of seeing a contour appearing, actually, I mean, it is smaller than the corresponding weights that appear here, which is exponential minus 2 beta times the length of the contour. So okay, okay, and maybe I should define what's the length of a contour. It's simply its cardinality when the contour is seen as a set of edges. Okay, and maybe just to, okay, I won't prove it straight away. I will first deduce positivity of the magnetization from this. But let me explain where this thing comes from. Okay, it is just that if you look at our modified Hamiltonian, I can rewrite it. I mean, it's really, I say that it's minus 2 beta times the number of disagreements. Okay, and a disagreement between neighboring speeds is really a green edge. So it's minus 2 beta times the number of green edges, and the number of green edges is just the sum of the length of the contours. So this is the sum from n equal 1, well, maybe not n, maybe k equal 1 to n sigma of oh, no, maybe it's better to write it like this, sum of gamma in gamma sigma of okay, so the Hamiltonian, it's just minus 2 beta times the sum of the length of the contour. So like the price of a contour is minus 2 beta times its length when you see it, what really appears in the exponential. So everybody agrees with this formula? Okay. So how does this imply our result? Well, you see, okay, we are looking at the spin at 0, and we are looking at the probability that this is minus. So for the spin at 0 to be minus, basically, I mean, I have to, Okay, to look at the spin at 0, I have to travel from the boundary and look at how many green edges I cross. Okay, if I cross an even number of green edges, then the spin is plus. If I cross an odd number of green edges, then the spin is minus. And the parity of this number actually will not depend on the path I choose to go from the boundary to 0. If I take a path such that the number of crossed edges is minimal, this number of crossed edges, it will really be the number of contours that enclose the origin. Okay, so what I get from this is that if the origin is enclosed in an odd number of contours, then the spin is minus. If the origin is enclosed in an even number of contours, then the spin is plus. Okay, and actually we will not really need that. What we will say is that just if the spin is minus, then the origin has to be enclosed in at least one contour. Okay? Because if it's not, then there is a path from the origin to the boundary that does not cross any green edges. Okay, this path might, okay, so there is a subtlety here that our path, they are allowed to use these diagonals. Okay, like when you apply this transformation rule, what you're basically doing is that you're kind of changing the structure of the graph. Okay, you're adding the diagonal here. You're allowed to travel this way. Okay, but this is okay. So yes, the important thing here is that you agree with this fact. So I just wanted to make lots of. Okay, I said more than necessary just to say that really you can compute the spins exactly looking at the contours, okay? But here we don't really need all of this. What we need to say is that sigma 0 is equal to minus. This event is included in 0 is enclosed by a contour of gamma sigma. Okay, now I will write just gamma bar. This is just the set of vertices enclosed by gamma. Okay, when I have a contour, basically it splits ZD into two. Gamma bar is just the finite part. Okay. So, because of this, using a union bound, what I can say is that the probability that sigma 0 is equal to -1 this is smaller, okay, than, well, so this event is just the union over all gammas that include 0, that gamma belongs to big gamma. Okay. Write it. Okay, so this is the sum over gamma such that 0 belongs to gamma of mu lambda beta plus, and then I get gamma belongs to gamma sigma. Now I can use the lemma, which we have not proved yet. Okay, and now to conclude, I just need an argument that helps me to enumerate the number of contours of a given length that enclose 0. Okay, because this thing here, okay, it is just the sum from n equal 2 to infinity. Well, okay. Of C2n exponential minus 4 beta n. Okay, where C2n is the number of contours of length 2n that surrounds 0. Okay. Well, what's important here is that the bound we have does not depend on lambda, the box we are in. And, well, the reason here is that, okay, when I looked at contours, I didn't even specify that the contours have to be in the box. Okay, so of course, when I'm using Peier's bound here, this bound is completely stupid when gamma is not in the box. You know, when the contour is something that does something like that. But it still remains valid, and well, it gives me an upper bound. Okay, and it actually gives me the reasonable upper bound, which is an upper bound for every box. So. Okay, so this is where the step where the dependence in lambda goes away. Okay, I'm just summing over every contour here. But if you prefer, you can sum over contours that are included in gamma. Okay, so gamma subset gamma. And then just bound the sum above just by taking away this restriction. Okay, so now if I'm not mistaken, what we have is that C2n, okay, so I'm trying to make something, to have something which is not too bad as a bound. So well, the thing that if you have a contour that encloses 0, then it has to have an edge at the left of 0, okay, that just crosses the x-axis. So we just consider this leftmost edge here. If the contour has length 2n, then this thing, so this is j minus 1/2. Okay, this is j. This is j plus 1/2. No, j minus 1/2 minus 1/2. J minus 1/2. J G minus 1/2. Now this J, it has to be in 1 n minus 1. Okay? Just because, like, if this edge is here, the smallest contour surrounding 0 then would have cardinality 2j plus 1. Okay, so there you get n minus 1 for the choice of j, okay, which is. Then you have 2n minus 2 steps where you have 3 choices. Okay, this is the first step of the contour. Then you can just do whatever you want. I mean, each time you have 3 steps because it's 3 choices because you cannot backtrack. Okay, and this last edge you have no choice because it has to close the contour. Okay, so I think this is fine. You can probably get better, right? Yeah. Okay. No. This is, yeah. I think this is. So what you get is that this is smaller than sum from n equal to beta. C n minus 1, 3 to the 2n minus 2, exponential minus 4 beta n. And this is what I will call delta beta. And we are pretty much done. When beta is sufficiently large, delta beta is smaller than 1. Okay, and then you can use dominated convergence to show that delta beta, in fact, converges to 0 when n goes to infinity. Okay, so this is the part when we use that beta is large. Okay, all I said before is, I mean, this Pyre's argument is true for every beta. Okay, it's the only place that I need where I need beta to be large is here, and it's quite crucial. I mean, you know that the probability of being a contour decays exponentially in its length, but there is a competition because, yeah, you have to pay an exponential price to get a contour of length n, but you have an exponential number of possibilities for having a contour of length n. Okay, and depending on who wins this competition, I mean, basically your sum will be finite or not. Okay, and when the sum blows up, I mean, basically you cannot, this analysis don't tell you very much, okay? I mean, basically it kind of tells you that taking the union bound here is a bad idea, okay, because these events are very far from being disjoint. So there is also, I mean, I don't know. So actually, you can refine, okay, I will not tell you how, but you can refine a bit this argument. And what you can say here is that, in fact, you don't need in order to have plurality of, I mean, here to have multiplicity of Gibbs states, you need delta beta smaller than 1/2. Okay, because you want the magnetization to be positive, and you know that the estimate you have for the magnetization is that it's larger than 1 minus 2 delta beta. Okay, what I claim here is that if this sum is finite, you have multiplicity of Gibbs states. Okay, and the reason is that if you're a bit more careful, you can prove that if the sum is finite, then the probability that 0 is not enclosed by any contours is uniformly positive. Okay? And if you think about it, like if 0 is not enclosed by any contour in the limit, it kind of implies that the plus Gibbs states and minus Gibbs state cannot look the same. So even without reasoning on the magnetization, if 0 is not in a, okay. Basically, if there is a possibility that 0 is not enclosed in a contour, then this means that basically what you're seeing is a sea of pluses with islands of minus around. And okay, you have, okay, the picture is not very good here because on these islands of pluses, you have lakes of, on these islands of minuses, you have lakes of pluses and on which there are, okay. So it's a really, I mean, you have lots of depth in the picture, but yes, the thing is, if you have this picture of a big ocean of pluses with only islands of minuses, then it already implies that the two Gibbs states are different. Okay, so was this clear? Now we need to prove Peyer's argument. So any questions so far? Okay. So I will give you a proof, and then, okay, so maybe I will put some exercises here. So an exercise is give a bound on beta c using this argument. And the second one will be adapt the proof I will give you of Peyer's argument to prove that, in fact, you have mu lambda beta plus gamma belongs to gamma sigma. And this is smaller than exponential minus 2 beta gamma over 1 plus exponential minus 2 beta gamma. Okay, just saying that if you want, you can improve a little bit this bound. And if you put it there, maybe you get a tiny better estimate for beta c. Well, the idea that it's not crucial because the bound you get is not tight in any case, but I think it's, okay, well, this is always good to do a bit of computation, and maybe this is good so that you revise Peyer's argument. You put your hands on it. So I will just give you this not optimal proof, and then you can try to improve it a little bit. Okay, so okay, so okay, let's assume that gamma is enclosed in the box. Okay, so this gamma bar, I mean, this is the set of sides that are enclosed by gamma. So let's assume that this is included in the box. And now the idea is to look at a spin, I mean, what we are looking at is this thing is a quotient, okay, and well, the idea is we want to show that the numerator is smaller than this times the denominator. And then we will be done. And in order to do so, what we are going to do is rewrite the denominator to make this factor go out. Okay, so now you see that because of what I had written before, okay, you already have this factor in the numerator in the sense that, well, basically, on all the sigmas that are in the sum in the numerator, you have gamma, which appears there. And, okay, so here maybe I should put gamma prime so that, because I have already. So I have to find a way to take it away, in a sense. And the idea is to consider a spin bijection, which will have the following effect on the contours. Basically, we'll just keep all the contours the same, but it will make gamma disappear. Okay, of course, it will just work if gamma is present in the contour configuration in the first place. And it will have well, not a very, okay, if gamma is not present and you have, then it has a totally different effect, but this is not really important because we are just going to apply it on spin configuration for which gamma is present. So, okay, so what's this modification? So, I mean, what we want to do is basically to say, okay, if we have spin disagreements on all edges in gamma, we want to make these disagreements disappear, and we don't want to change the state of the other edges. So what we can do is just flip all the spins that are inside gamma and keep the rest the same. If you do this, well, then outside gamma, of course, you will not have changed the state of the edges, but it's also true inside gamma, because if you have two spins inside gamma, well, both spins will have changed, so the disagreement structure remains the same. Okay, so a good definition for this is to say that the spin at x is equal to minus sigma x if x belongs to the interior of gamma, and it's equal to sigma x if x belongs to gamma. Okay, and my claim is that if gamma belongs to gamma of sigma, then gamma of sigma E gamma sigma is equal to gamma sigma minus gamma. Okay, so, I mean, why this is true, I won't write the proof of this claim, but the idea is that if you look at the set of edges, the set of green edges, this is just what I've said. I mean, the set of green edges for this configuration, it is just the original set of green edges minus the edges of gamma. Okay? Now the idea is that if you take away one contour, basically, it doesn't affect the rest of the contour structure. Our deformation rule is such that if I take one contour away, the other contours are not modified. Okay, so a consequence of this, it is that h lambda beta plus of epsilon gamma of sigma, it is equal to h, sorry, this is equal to this minus 2 beta gamma. Okay, I'm just applying the formula below. And I have a bar here and I have a plus here. I'm just applying this. This and this. Okay, so therefore what I have is that, okay, maybe I can erase this finally. The sum over sigma such that gamma belongs to gamma sigma of exponential h plus lambda beta sigma. Well, this is equal to exponential minus 2 beta lambda times the sum over sigma of exponential gamma lambda beta plus okay, and now yes, I can say that this is smaller than z lambda beta plus. This is simply because my transformation here, okay, so this thing, it's equal to the sum over sigma prime such that gamma belongs to okay, I can just make a change of variable in the sum. Okay, yeah, this thing is not very explicit. I mean, it's not very explicit what this set is, but the only thing is that it's a subset of the whole space. So. Okay, and this ends up the proof of our claim, and therefore we just completed the proof that there is magnetization at low temperature. Positive magnetization at low temperature. Okay, so any question about this argument? Okay, And when I say this can be adapted to other models, the idea is that there are other cases where you can find a transformation of your Hamiltonian, so that basically you can get a factor out and get bounds for certain types of events. Okay, so it's a quite general idea. Okay, so far we have just proved things in dimension 2. Yes, I mean, if you want to reason in dimension 3, basically you can, well, what you can do is that instead of doing the drawing I've done in dimension 2, you make it in dimension 3. Then these green lines, they become green squares. Okay, so your contours, they kind of become surfaces, and you have to count your surfaces. You have to be a bit rougher. There is no clear rule for there is no separation rule when you come with surfaces. There is no nice separation rule. So you have to find another way to basically overcount everything. And this can work, but we are going to take another path. And this other path is just to say that, well, if you fix beta, and you look at the magnetization as a function of the dimension, then it increases with the dimension. So if you prove that it's positive in dimension 2, then it's positive for every dimension. Okay, so for the larger than 3, we prove that m star beta d is an increasing function of d. And okay, this is kind of intuitive in a sense when you take the dimension. Okay, when the dimension is larger, every spin feels the influence of more neighbors. Okay, so I mean basically. If you look at, okay. So. Let's say that this is a 2n by 2n cubes, okay? And this is its, this thing here, it's the equator of my cube. Okay, and let's imagine that I have the Ising model with plus boundary condition on this cube. Now, if I look at what happened on this slide, on this slice, what I have is it's basically like a two-dimensional Ising model, except that I also have influences of what's immediately above and below me. And what's above and below me, well, it's more likely to be plus than minus because they have plus boundary condition. So it should help me to be plus. Okay, and the way to prove this rigorously is, well, basically to find a way to interpolate between the two-dimensional Ising model and the three-dimensional Ising model. So, okay. How are we going to do this? So, modulus. Okay, so let me do it just as I have written it. So let's consider, okay, gamma now is just minus n to the t. Okay, and I will just consider gamma bar, which is gamma intersected with z2 times 0 to the g minus 2. Okay, so this gamma bar, it's my this green slice that I've. Okay, and I define now an Ising model on gamma, but where I have two parameters. So this beta prime, it's not the magnetic field, okay? There is no H in this lecture whatsoever. It will just be that the beta that an edge feels really depends on the edge. So what should be here? So here I get beta times the sum over E in E gamma bar sigma x sigma E plus beta okay, sum over x in gamma plus beta prime sum over E in E gamma minus E gamma sigma E plus beta sum over x in gamma minus gamma bar y in okay. Okay, so just a long formula to say something simple. What I'm going to be doing is to say, well, I'm going to put an interaction beta on all the edges that are either green-green or green with a boundary. And I will put an interaction beta prime on all the other edges. Okay, so, and I define mu beta beta prime accordingly. Mu lambda beta beta prime plus it's equal to just this. Okay, so now an observation is that if I look at the spin at the origin, okay, if beta is equal to beta prime, well, this is just the Ising model on lambda. If beta prime is equal to 0, then really the magnetization at 0 is the same as the magnetization at 0 for the two-dimensional box. Okay, the reason is that basically if I put beta prime equal to 0, my measure is just, well, two-dimensional Ising model on the green on the green part, and independent plus and minus 1 spins elsewhere. Okay, so this is equal to, okay, so this tends to m beta t, and this tends to m beta 2. Okay, maybe okay. To really prove that this is increasing in d, I should do it with d and d minus 1, but the reasoning is exactly the same. Okay, so if I want to show that this is larger than this, I just need to show that this is larger than this. And if I want to show that this is larger than this, well, I just need to show then this is non-decreasing in beta. Prime, sorry, non-decreasing in beta prime. Okay, so that it's larger when beta prime is equal to beta than when beta prime is equal to 0. Okay, and now I guess this is something that you should, okay. This is basically something that we have done last time. So what would be the idea to prove that this is monotone in beta prime? So you can do the usual thing that you want to do when you try to prove that a regular function is monotone. Just compute the derivative, and when you compute the derivative, what will appear will be some covariance, which you will be able to you will be able to prove that it's positive using GKS inequality. So here it's the part where, well, it's important that we have proved GKS inequality in a general setup because we are going to use it for a model where the beta actually depends on the edge. Okay, but if you remember, the setup in which we proved GKS was much more general than this. Okay, we included even interactions on triplets of sites if we wanted. Okay. Okay, so if you compute this derivative, basically you have two things appearing. So, okay, when you take the derivative with respect to beta, basically you have things that come down of the exponential. And, well, this thing is just the sum over edges of something. Okay, so I don't tell you who E is, it's not really important. I mean, basically, E is just, yeah, everything that I have here. So I can have edges here outside of the green thing and interaction with the boundary as well. When I take the derivative with respect to the numerator, I will have sigma 0 times sigma E. Okay? Then I will multiply it by the exponential and divide it by z. So this gives me lambda beta beta prime plus. Now, when I take the derivative with respect to the denominator, well, I will get a z square here, and then I will get two sums above, so this will give me exactly this. Okay, and now what I have is that this is positive by GKS. Okay, sigma E here, I mean, it's either the product of two spins or just the product of one spin, depending on whether you're considering a boundary edge or an edge which is inside. Okay, but if it's just one spin, I mean, what's important is that the sign is positive here because the boundary condition is plus. Okay, yeah, I'm just summing over all the edges with parameter beta prime. Okay, so I've not been I've not put lots of details here, but it's exactly the same computation as last time, and it's very similar to the computation we've seen on the first day of the study of Ising model. Okay, so with this we get that well, magnetization in the dimension larger than 2 is larger than magnetization in dimension 2, and therefore, in particular, you get that well, the magnetization tends to 1 in every dimension when beta goes to infinity. Okay, so now there might be, you might have other, okay. We have proved that there are 2 Gibbs states. The question might be, are there any other Gibbs states than these 2? And the answer is quite simple, it's yes. It really depends on how you define Gibbs states. And here maybe, I should refine a bit the definition we have given. But basically, so Gibbs states for us, it was just the limit, the infinite volume limit of Gibbs distribution. So it's exactly this, but what I'm going to say is that we can also allow for random boundary condition. Okay? Because basically, a Gibbs state formally is not exactly this. A Gibbs state, it's basically it's a state which satisfies the Markov property. Okay, and this is equivalent to what I said. So basically, a state, it's something which is such that if you condition to all the spins outside of a box, and you look inside, what you obtain is the Ising model with boundary condition, which is given by what you have outside. Okay, but you need some measure theory to be able to make this conditioning work. Okay, so with this consideration, what you have is that well, convex combination of Gibbs states are Gibbs states. Okay, so but these are not very interesting. So the question is: are there any Gibbs states besides these combinations? And the answer really depends on the dimension. So in dimension 2, the above are the only Gibbs states. Okay, and another way to say this is to say that the plus and the minus Gibbs states, they are the only ergodic Gibbs states. So what ergodic means is that if an event is invariant by translation, then it has probability 0 or 1 under the Gibbs state. If D is larger than 3, then the above are the only translation invariant Gibbs states. Okay, so what this, and when I'm saying this, of course, what is also true is that there are also Gibbs states that are not translation invariant. So maybe let me explain how in dimension 3 you may obtain Gibbs states that are not translation invariant and not the plus and not the minus Gibbs states. So let us start with this cube. And let us choose, say, minus boundary condition in the lower half space and plus boundary condition in the upper half space. Okay, and the idea is that, well, when beta is high, okay, well, Peyer's argument basically tells you that it's very costly to construct interfaces between plus and minuses. Okay, it costs basically beta times the area of your interface, and then the combinatorics tells you that the number of bubbles of a given area grows exponentially, but smaller than exponential minus 2 beta if you take beta sufficiently large. So what you will see is basically a sea of pluses here with some minus bubbles, a sea of minus here with some plus bubbles, and in the middle you will see an interface between plus and minus. Okay? And this is not really the end of the story, because this thing could work in dimension 2 as well. So the idea is that for this to give you a non-trivial Gibbs state, I mean, you want to make sure that you can see this interface in the limit. Okay, and basically to understand this, you have to reduce the problem one dimension. So when you look at this, when you want to understand this interface, basically Well, it will be something that kind of goes up and down, okay. I don't know, yeah, it's. Okay, and okay, what you want to basically show is that this thing remains flat in the limit, when the box gets larger. And the reason why it gets flat, heuristically, is also Peyer's argument. Because, okay, I don't know if you do some hiking, well, maybe now you use smartphone, but in the days if you look at a topological map, okay, when the altitude varies, you have these level lines that have to go, okay. And the idea is that for this interface, I mean, each time you have a level line, so each time something goes up by 1 or by -1, basically, on the side of the line, okay, you have these plaquettes of disagreement. So a level line in the Hamiltonian, it has a cost which is proportional to its length. Okay? Now this is just a big stretch of the imagination, but the idea is that using Peyer's argument again, you can say that you have no long level lines. What you see is something which is basically, that looks empty from far away, and you have some small bubbles of level line. And this basically tells you that what your interface is really something flat with some small local perturbations. In particular, when you take the limit here and you look at the system from zeros, well, you see something in the limit where you see that an ocean of plus above and a sea of minus below. Okay, and for this, really, you need d minus 1 to be larger than 2. Okay? In dimension 2, this doesn't work. The reason why you have uniqueness here is that if you take this same plus and minus boundary condition, and you look at the interface between plus and minus, now if you think a bit about it, if you just ignore all the other bubbles and stuff like that, this interface is something that looks very much like the graph of a simple random walk. Okay? The idea is that it's penalized by its length, but the length is almost the same for every interface. So basically, it's a theorem, and it's not exactly easy to prove, but at every temperature, when beta is low, okay, when you're in the low temperature phase, this thing rescales to a Brownian motion. So in particular, if you look at a small, when you look at local functions, okay, you're looking at things that are around the origin. You know that this interface, it will typically be at distance square root of n from the origin. So if you take exactly this boundary condition, what you will see is that with probability 1/2, you will see an ocean of plus, of minus, okay, like here, and with probability 1/2, you will see an ocean of plus, depending on whether on the macroscopic level, your interface is above and below, or below. So that if you take this kind of boundary condition, basically, okay, on dimension 3, you get something non-trivial. In dimension 2, you will just get this convex combination with lambda is equal to 1/2. Okay, so, okay, all of these are complicated stuff that were proved in the 80s, but okay, I think they are interesting, and if you're curious, and in some years you want to look at the literature, this is something that has been proved, and the proof are nice. So. Okay, so let's stop here. Any questions?